Yeah. Do you see the title slide?
Yeah. Yes, we do.
Okay. So hello, everyone. My name is Vasilii Mohsin. I'm an industrial PhD student at Volvo Cars. My today's talk will be a little bit more applied compared to other speakers, but excepting Khaled, he also did an applied research, and it's a little bit related to Jennifer's talk, first talk in the beginning of the session. So I will talk about anomaly score evaluation and driving scenarios, in particular using autoencoder-based approaches. We did this small project with my supervisors Miroslaw and Darko Duruisic from Volvo Cars. So when we talk about perception systems in the automotive industry and self-driving cars, we talk about mostly deep learning, perception, for example, object detection algorithms and semantic segmentation. And these deep learning models, they are known to have some problems, and one of the problem is called distributional shift problem. It's related to when we train out the model with some data distribution, and if we want to predict something in the future, we want to have this new data coming also from the same distribution. But if it's not the case, then it will the model will output some erroneous predictions. For example, if we train our model with our perception algorithm on Swedish roads, and during the training, our model have seen mooses a lot, and during runtime it will predict mooses with high confidence. It haven't seen kangaroos on the Swedish roads during the training, and during the runtime, it will output something unexpected, and in the worst case, the prediction will have a high confidence. Like, for example, on the right side of the slide, you can see that the kangaroo is predicted such as a plastic bag almost with 100% confidence. And this is obviously not a desirable behavior for our perception system in cars. And we called this set of images anomalies because there are anomalies with respect to what we have seen during the training. And talking about different types of anomalies in driving scenario images, we can distinguish two general groups. On the left side, you can see the first group is the context anomalies, when we talk about the whole picture. And for example, it can be a new landscape scenario, consider it as anomaly. If we were trained our deep learning model on the highway roads, and once we go into the into driving in urban scenarios, most probably it will have a much lower performance. So in this case, new landscape is our context anomaly. On the right side, you can see an example of a second group of anomalies in driving scenario images, which called semantic anomalies. Semantic anomalies, it's about some particular information presented in the image or in this scenario. For example, new objects can be considered as anomalies. If we, during the training, we were driving around empty highways. It's an imaginary situation, but let's imagine this without any vehicles. But if we want to use this deep learning model with on the highways with vehicles, then it will not detect cars for us, obviously. And in this case, new object type, which is vehicle in this case, is considered as semantic anomalies. Semantic anomalies can be also an unusual location of the object. For example, if during the training we have seen the car in the bottom part of the image of the camera, and if during the runtime it suddenly appears somewhere in the top right corner of the image, it can be also considered as semantic anomaly. And the second group, semantic anomalies, are known to be more challenging task. To detect the semantic anomalies is more difficult than to detect context anomalies. And in our project, we have focused on this second type of semantic anomalies. We focused on this imaginary situation when we had empty highway roads as a normal set of images and highway roads with vehicles as anomalies. Just to start with a little bit easier task and moving on with a more complex scenarios. So when we talk about images and anomaly detection on images, the autoencoders, they are usual models which are used to detect anomalies in images. And what is the autoencoder? It's a particular type of neural network consisting of two parts, encoder and decoder. Their main goals is to perform dimensionality reduction on the images, but they can be also used for anomaly detection, and there are two approaches for this. So you can see that encoder decode the input image into some lower dimensional representation, which we call bottleneck values. And it tries to reconstruct from these bottleneck values using decoder the original image, and we get the output image. And it is trained to minimize this reconstruction error between the output and input image. And the idea behind the two approaches is that we first train the autoencoder with some particular training distribution images, and during the testing time or runtime, if we feed this autoencoder with an image coming from completely different distribution, then the reconstruction error will be higher because it will not be able to reconstruct unseen images as good as it does for training data distribution images. And this is the first approach related to reconstruction error. We can use reconstruction error as an anomaly score. The higher reconstruction error is, the higher the probability that the input image is anomalous. And the second approach is to use this lower dimensional image representation in the middle, in particular bottleneck values. We can compare these bottleneck values to the bottleneck values of training distribution images, and if they're very different, then the input image is considered as anomaly. So yeah, we have considered these two approaches for anomaly score evaluation, reconstruction error in bottleneck values. And going to the experimental simulated data, we started with simulated data because it is obviously easier. We have generated using Pro-Sivic platform two sets of images. One, as I mentioned, was normal set of images, which were our empty roads. And the second set is anomalous set, when we had the same highway scenarios, but populated with different kinds of vehicles, cars, motorcycles, and trucks. So in this case, we consider the presence of vehicle as an anomaly, and therefore we call this set as anomalous. And yeah, the picture is not showing as it was supposed to be showed, but anyway, so this is the autoencoder architecture which we used in our experiment. It consists of three convolutional layers in the encoder part and three deconvolutional layers in the decoder part. And in the middle, we have a bottleneck values, and this the size of this bottleneck values vector is 512. So we compress the input image, all these pixels, to this compressed representation of the bottleneck values. So we trained this autoencoder with a set of normal images, which were empty highway roads, and then tested it. We computed anomaly scores for different set of normal images, empty highway roads, and also we computed anomaly scores for highway roads with vehicles, and we tried to estimate the anomaly detection performance, how well we distinguish between this normal and anomalous set of images using this trained autoencoder with two different approach. So this is the results which we got on a simulated set of images. The left and the middle picture, we plot the anomaly scores distributions for two different set of images. Blue graph corresponds to normal, to anomaly scores for normal images, and orange one corresponds to anomaly scores for anomalous images. And for both approach, reconstruction error on the left and bottleneck values in the middle, we can more or less well separate these two different distributions, which means that we can perform anomaly detection with a high performance. And in order to estimate numerically this performance of anomaly detection, we plot on the right side of the slide receiver operating characteristic curves. This is a special methodology used in machine learning to estimate the performance of binary classification task. And our anomaly detection is indeed a binary classification task, because we predict either the input image is anomaly or not. And depending on choosing the threshold, as you can see on the distribution plots, choosing a different thresholds on the anomaly score, we can get different anomaly detection results from. So the same image can be detected as anomalous or not, depending on the selected threshold. So varying this threshold on anomaly scores, we can get different true positives and false positive rates. And we plot these true positive and false positive rates for each of the, for varying a threshold. We plot this on a 2D plot with two axes corresponds to true positives and false positive rates. And we get this receiver, so-called receiver operating characteristic curves. And usually the area under this curve corresponds to performance of classification task or anomaly detection in our case. And the closer these graphs goes to the point, the upper left point, which corresponds to 100% true positive detection and 0% false positive detection, the better the performance is. So we measured these two performances for two different corresponding area under this receiver operating curves, Roca, Hook, and Short. You can see it in the bottom of the right graph. For reconstruction error, it's 0.97, and for bottleneck values, it's 0.94. And if we look at the actual plots on the red one and on the green one, red one is for reconstruction error and the green one is for bottleneck values, we can so we want to focus on the upper line, which corresponds to 100% true positives. We will always want to have this 100% true positive rate detection because it's related to the safety. We always want to detect all the anomalies, but depending on the approach, we get different false positive in this case. And as you can see, when we have 100% true positive rate, we get more than 60% false positive detection for reconstruction, which is not good. It means that we detect all the anomalies, but in the same time we detect a lot of false positive detections. But the bottleneck values approach corresponding to this metric, which is false positive detection at 100% true positive detection, is better because we get less than 20% false positive detection in this case. So this was about results on simulated data, but our ultimate goal, of course, is to show how it is working on the real data. So we selected this more or less similar looking data set. It's called Kitti, German data set, with empty roads and roads with cars. Obviously, the scenario or ground scene is looking very different because we have forest here, and in our simulated data set we didn't have such a lot of green colors in the images. But anyway, we try to be straightforward and apply the already trained autoencoder on simulated data and try to estimate anomaly scores on the set of real images for normal and anomalous images, for empty roads and roads with cars. And in this case, as expected, we got very bad results. These two distributions of normal and anomalous images, anomaly scores, they are similar, and receive operating curves reflects the same, that the performance of anomaly detection on real set of images. Just taking the same autoencoder trained on simulated data, it doesn't work at all. So we have almost random guessing when detecting anomalies. But we also retrained this autoencoder with a new set of real images with empty roads, and estimated anomaly scores in this case, and we got these pictures. For the reconstruction error, it a little bit improved anomaly detection. We can see that two distributions of anomaly scores, they a little bit shift out of each other, but for bottleneck values, distribution again looks the same, and the receive operating curves and Roca-Hawk metrics, they reflect the same behavior. So for the bottleneck values, it stayed the same, almost random guessing when predicting anomalies. But the reconstruction error, yes, a little bit better, but still 0.6 is not a good Roca-Hawk metric for anomaly detection. So a few words in the end about where these anomaly scores can be used and how they should be used. And usually the proposed scheme is to use so-called safety cage architecture. It's when we have our perception module based on the deep learning algorithm, which outputs perception results. But in the same way, we want to estimate the anomaly score for the input data. Therefore, we build upon this perception model, we build anomaly detection model, which is based on autoencoder in our case, that outputs anomaly scores. And then we decide, based on these anomaly scores, depending on the selected threshold, do we want to trust or not this prediction? And if we trust, then it's okay, we continue as usual. And if we don't trust, then we raise a flag that anomaly is detected and we do some kind of a safe action. For example, we switch off the autonomous mode and perform a hard braking of a car, for example. This is how anomaly detection, how anomaly scores can be used in the real automotive application. And the main point here that the performance of the whole safety cage, it mainly depends on the performance of the anomaly detector. So this on the anomaly detector and driving scenario images is very important. So yes, to conclude, we have demonstrated and evaluated performance of anomaly detection in driving scenario images with simulated data using autoencoders approach. So we showed how we can calculate anomaly scores. We showed how we can estimate the performance of anomaly detection with these calculated anomaly scores. Then we moved further to using the real data and experimented with the real data sets. And straightforward approach, they doesn't work out of the box like we expected, of course. Without retraining, it shows very bad results. With some kind of retraining, the same autoencoder shows slightly better results for one of the approaches. And the further goal, of course, is to improve the performance of anomaly detection on real images in order to be able to show of the how it can be done. most probably we should experiment with a more complex autoencoder architecture, because the one which I showed you in the slides is a really very simple autoencoders, which is suitable for using with simulated data, but real data, it has a more complex structure. Obviously, it has more local pixel intensities variation and so on. So we have to use more complex autoencoders in this case. And also to build a bigger picture, to make a full picture of this technology and to show a full proof of concept, we need to consider, of course, more complicated anomaly scenarios, considering unusual objects or animals as anomalies, because this example which we showed to detect highway roads with cars versus empty highway roads and highway roads with cars as anomalies, it's not very like applicable or interesting, of course, from the automotive perspective. So we have to play around with different types of anomalies also. Yes, so that's it. Thank you for your attention.